In this section, we're going to start digging into MPLS, or multi-protocol label switching. So as we go through the multi-protocol label switching section, we're going to be hitting quite a few things. We're going to start off with introducing MPLS, and there's a lot of parts to understand about MPLS. We'll take a look at the high-level theory, then we'll take a look at breaking down a label flow from the incoming provider edge router to the outgoing provider edge router, and all the things that could happen. And we're going to take this in different steps. So the way that I'm going to roll out the course is in such a manner that we're building off of what we learned in previous videos. So I'm not going to dive super deep, super quick. It's going to be basically, if you don't know what MPLS is, that's okay, because we're going to cover that here. But basically what we're going to do is cover the foundations, and then we're going to build on top of each video on top of that, and with a practical rollout. I have a solid use case for all of this to be rolled out with. We're going to take a look at how MPLS works. Now, once we understand how MPLS works and the background to it, we'll then be able to dig headlong into Label Distribution Protocol, or LDP, which is pretty much the key piece to MPLS. It is the L in MPLS, label. So we're going to be taking a look at that in a lot of detail. And then we're going to finish this section up with MPLS traffic engineering. Now, MPLS traffic engineering is going to take MPLS to the next level. Now, for those of you that come from a routing and switching background that don't work on the service provider side of the house, this is going to definitely dig into areas of MPLS you may never have seen before. Now, if you've never seen MPLS at all, then you're going to be learning pretty much the entire gamut of MPLS itself. And like I said, as we go through, I'm going to build it up to where how MPLS is utilized, because at the end of the day, what MPLS is really doing is providing the transport between your sites. That's really all that it's doing. And how it does that determines how the service provider will roll it out. We'll take a look at exactly how that works and the details behind it. But it's really important to understand how MPLS itself works. So we're going to go from a pretty much a before and after, or before, during, and current type of rollouts that you could see with MPLS. And I think that will really efficiently draw the picture as we progress through here. So one of the things that you'll be very happy to know is just about everything that we're going to be covering MPLS in this particular in the core exam and in the edge exam will put you in pretty good shape to, if you're interested in, if you're utilizing these videos as a segue to go to CCIE, whether it's routing and switching a service provider. This will be a good segue, because we'll be taking a lot of the stuff that isn't covered in CCNP for routing and switching and is covered in CCNP service provider. So you'll see how that comes into play and all that good stuff. So what we're going to first take a look at in this on this slide here is what the technologies were before MPLS came into the mix. So we're going to take a look at a traditional telco and an internet service provider, or an ISP. We'll take a look at modern service providers. We'll take a look at the Cisco IP next generation network architecture, why that is so important to understand. We'll take a look at SONET and SDH, DWDM and ROADM, as well as IP over WDM. Then we'll dig into an MPLS introduction. So now once we've gotten through the before MPLS came out, then we'll take a look at what is MPLS. So we'll describe MPLS at a high level and how it forms based on the label. Describe the benefits of MPLS, the different router types that you'll see within MPLS, the control and data plane, the FIB and the LFIB, as well as describing the MPLS label. We'll explain how an IP packet is forwarded using MPLS label switching. We'll describe actually the funny thing about it is MPLS label switching is actually saying the last two letters first, so it's multi-protocol label switching, So it's kind of redundant. It's like NIC card. Well, that doesn't make sense because you're saying network interface card, card. We'll take a look at the label stack and how that breaks down, as well as applications in a service provider, describe the support for unicast and multicast routing. And then once we have that understood, then we'll be able to break down the VPN aspect of MPLS, which is really what MPLS is allowing us to leverage, right? So MPLS is just a transport. It's how we get traffic from the incoming provider edge to the external provider edge, or the egress PE, if you will. So we'll take a look at the support for virtual private networks, and that'll be for layer 3 and for layer 2. We'll take a look at optimizing MPLS VPN with traffic engineering. How can you manipulate how the traffic will forward through the network? Because by default, MPLS or LDP the label switch paths will typically follow the shortest path from the provider edge to the provider edge. Now we're going to have 6 routers in our core. If you've been following along this course from route to advanced route, we're using the same topology over and over and over again, so that it's easy for all of you to keep up with this. We're not changing new topologies every time. It's one big topology for all 4 courses. So that's going to help everybody understand it. So if we have a situation where we're following the shortest path between R1, or I should say like XR3 and XR1, which would be XR1 to R1 to R3, or I'm sorry, XR3. A situation like that, and if you don't know what I'm talking about, I'll show you the topology here in just a moment. Traffic engineering will help us determine how we get through the MPLS core, not just based off of the shortest path. And we'll take a look at as to why that is such a big deal. Then once we talk about traffic engineering, we'll dig into quality of service. Quality of service is going to be the back half of this course and is going to be heavily leveraged with inside of MPLS. Now, technically speaking, quality of service and MPLS are 2 different technologies, and they're 2 different. They're mutually exclusive. You don't have to have MPLS to run QoS, and you don't have to have QoS enabled in order for MPLS to operate, or vice versa. So QoS will work if MPLS is not enabled, and vice versa. So we'll take a look at exactly how that comes into play, and just to make sure that we understand the details behind it, one of the things that I'm going to be doing is I will be spinning up a couple of very basic layer 3 VPNs and showing how traffic engineering and QoS will come into play. Now, there'll be basic examples, but it'll be showing you how all this stuff comes together. Now you might ask, well, why is that pertinent? Why does that matter? Well, the reason it makes a difference is because it's one thing to see provider edge to provider edge LSPs. Okay, that's cool. It makes sense, or at least it will down the road. But you might ask, well, why QoS? What difference does that make? Well, it's going to make a lot of sense if you're using MPLS for sensitive types of traffic. Let's say, for instance, you're using MPLS for inter-site voice over IP or video traffic. We'll take a look at exactly how that comes into play and how you would utilize MPLS for that. And then last but certainly not least, we will take a look at the interaction between MPLS applications. Now, everything that I've talked about so far, this is all the things we'll talk about. So don't expect to see all this stuff out of the gate right away. We're going to talk about how all this stuff works out, and we'll go through a deep understanding of how it comes into play. Because before any of you can really understand how MPLS is utilized, it's important to understand its use cases and its the methodology that's used to deploy it. So before we go off the deep end on MPLS, let's take a look at why we use MPLS. So we're going to first take a look at traditional ISPs versus traditional telcos. Well, in traditional ISPs, they provide internet access. That is typically what an internet service provider does. Now, it's not the only thing that they provide. They could provide other options. You also have traditional telco, which typically will provide you VPN, which you may not agree with that, and that is completely okay. You might say, well, telco provides me internet access. Telco provides me my voice over IP service as well. I have some sort of managed service. Well, they're more generic overview more than anything else than they are specific implementations. So typically, I don't have MPLS service here at home. I don't have BGP here at home. I just have a dedicated internet connection out to the internet. So that is ISP all day long. Time Warner is my ISP. Do I need anything else? No. Could I? Sure, if I want to pay for it. But I have no reason to. I have no other locations throughout in this country that I would want to route MPLS, at least here at home. Now, when it comes to modern service providers, this is what most of us will work with, and this is the part that really needs to be understood. So it uses an IP-based infrastructure. So we route based on layer 3, right? Well, it maintains only one technology aided by MPLS to support additional services. So you could, with implementing MPLS in your network, you could allow for internet access through the VPN or internet as a VPN. You could allow VPNs and a virtual private network. And let's not confuse internet in the VPN or internet as a VPN as it's to be mutually exclusive from VPN or virtual private network. The whole purpose of MPLS VPN is to make sure that my traffic from my company is not seen by your company and your traffic. So we are able to logically segregate customer A from customer B and customer A from customer C, etc. So we can logically separate all this stuff, and VPNs allow us to do that. One of the things you can deliver via MPLS is telephony service. So let's say, for instance, I have a call manager service that I would like to roll out. Let's say for the moment that I am deploying SIP, and I want to deploy that to my customers. Well, my customers require a certain guaranteed service, and MPLS allows me to do that because I can prioritize the traffic, which gives me quality of service. So QoS and telephony kind of play hand in hand, but it's not always just that. You could do several different aspects of it, but it really depends on the situation at hand and what services you require to run your business. That's the benefit of MPLS. It gives you the flexibility of rolling out multiple services to a single customer. So you could roll out unicast VPN, which is going to be similar to IPsec VPN, except for the fact that you can route using MPLS, where you can't really route with IPsec VPN because it's going to be unidirectional. You could if you'd like, but say for instance you were to throw your routing inside of a GRE tunnel, that would work. But most of the time, MPLS VPN is going to be a private service, which means it's going to be a different circuit, a different bandwidth connectivity, and it's not going to be going out to pure internet. Yes, you could get pure internet over your VPN. That is a commonly rolled out capability. But then again, it's one of those things that it's typically an additional service charge. So it depends on the situation. However, you can retain competitive pricing in the ISP simply for the fact that you can offer a wide range of services via MPLS that normally would not be able to be maintained. So, for instance, I could have a customer that comes to me and says, "Hey, Rob, we want to run multicast in between our sites. How would we do that? We already have MPLS. We don't want to go out and roll out, say, for instance, DMVPN. We want to leverage the service level agreement or SLAs that we currently have with you. How could we roll that out?" And I'm like, awesome. Yeah, totally can do that. You can totally run multicast VPN as an additional service charge, and it takes a little bit of overhead configuration. We won't be taking a look at that in this course. We will be taking a look at very, very basic, they typically call it the data and default MDT or multicast distribution trees inside of MPLS. We'll take a look at a very simple rollout of that. We won't be getting into any of the advanced like point to multi-point with the advanced like multicast LDP and stuff like that. We're going to have a PIM-aware core when we get done. We won't be doing multicast LDP, at least in this course. In future courses that might be covered. It includes additional developments. So you have WDM in the core for more core bandwidth. And this is where WDM or DWDM or CWDM, coarse wavelength division multiplexing, would come into play. And it definitely is supported, but this is more of a layer 1 feature for basically multiplexing multiple lasers over a single fiber to give you more bandwidth over that fiber cable. Now, that is typically in the core, and more providers, at least that I work with and that I've seen, are moving away from DWDM and they're moving over to Ethernet core. So they're going to have they'll more than likely still have fiber, but they'll be running Ethernet-based protocols inside of the core. Now that's not always the case, but it's more and more that I'm seeing that happen. Even with at the edge, they're making Ethernet end to end. So it's Ethernet at the attachment circuit or the customer to CE to PE connection. And it's also Ethernet in the core. So you're moving away from DWDM and things like that. Typically, if you're at least in my experience, your experience may be different. Typically, in my experience, your connections between your point of presence and the core, that is going to be where you're leveraging DWDM. And your routing between those, and you could be MPLS switching it as well. I've seen that as well. But at the end of the day, it's really boils down to how you're forwarding. That's something that has to be figured out. DWDM is still out there. It's still widely deployed. Do I have anything against it? No, not at all. It works. It functions just fine. We also have DSL cable and Ethernet on the edge. So I might need to still roll out those services to customers, and they're still widely deployed. More and more customers are rolling out to Ethernet because you get higher bandwidth. I've got some internet circuits and some Ethernet handoffs, I should say, that are gig capable at some of my stores. I have some of them at some of my corporate locations. I have some of them at some of my customers are running Ethernet at the edge. You might ask, well, why Ethernet? Because it scales really, really well, and it gives a lot of flexibility. So you can do either layer 2 or layer 3 handoff, and it works just fine, depending on the service you're purchasing from the provider. And then you have various wireless technologies. Now, I'm not a wireless guy for the most part, so you have the ability of having like some of your more popular carriers like Sprint and AT&T. They allow you to do cellular wireless. So you could have a cell phone service and be able to talk and have your home internet through the same carrier. It's two different technologies, and you're obviously not routing on the same wire. So these are different situations that are different services that the provider can allow you to purchase and be able to support for you. There's also the ability of the provider basically giving you a managed device. Like for instance, if you work in the enterprise space, you're likely utilizing a managed service for MPLS where the provider issues you a device that you install on your network, but they manage it. So managed CE, managed customer premise equipment. That is the most common design that I see. Most of my customers are managed CE, where the provider handles that, and which actually makes the benefit to the provider simply for the fact that I'm good with BGP. So if I'm running BGP between myself or between the provider and the customer, I'm guaranteeing that things are going to come up when that router spins up or that switch spins up and it forms a BGP pairing back to my provider edge, and then everything gets routed the way that it should be. I'm not having to walk a customer through configuring BGP or taking over a router because they goof something up. So managed CE is a very popular rollout model, but it's not the only model that's out there. There is still situations where the customer has enough technical expertise to be able to do that. Other wireless operations, the modem or the router could support a wireless card in it. So I know there are some providers that provide a customer premise equipment that both terminates their cable or DSL internet to a modem of some type, and then you also have a Wi-Fi adapter in there to give yourself give the location wireless access. That is a widely deployed capability, very popular, I might add. Now, one of the cool things about these technologies you'll see is both SONET and SDH. Now, SONET is US based and SDH is European, and you can tell by the E1, E4 versus the DS1, DS3. Now, a DS1 basically is a T1, a DS3 is a T3, and at the end of the day, they both get the job done. And you can see as you go down the line, an STS1 is a DS3, which basically is 28 T1s bonded together. And depending on the circuit size, as you can see, you go down OC1, OC3, OC12, OC192, etc. You see them, the bandwidth increases as you progress through, and that works out quite well. And you'll see that more often than not, that is a very common rollout. Now you could also see that on the right side under the SDH aspect of it, that they're pretty close in comparison. At the end of the day, it's up to whatever the provider's utilizing. Now, when it comes to DWDM and the ROADM, wavelength division multiplexing, or WDM, is going to be a capability of multiplexing lots and lots of lasers over fiber, which gives you a better bandwidth over that individual fiber. The ROADM is a similar capability, which basically offers you reconfiguration capabilities remotely. So think of this as SSHing into a DWDM device and reconfiguring it without having to send a technician out to the site in order to do that. Kind of how managed CE works in a way. Think of it like that. You also have IP over DWDM. Now, I'm not going to go into a ton of detail because this is, I won't say the industry is moving away from this, but I don't see this very often, is how I'll put it. And you do need to support the ITU-T G.709 standard. And as far to my knowledge, almost every Cisco router that I've ever worked with supports this. It depends on the card installed, but at least that's in the carrier grade routers. I should qualify that. Carrier grade routers are the ones that typically support this, and that's the only time I've ever seen it rolled out. You also have 10, 40, and 100 gigabit Ethernet. This supports full duplex operation only, which is obvious because it's gigabit. You preserve the 802.3 Ethernet frame format utilizing the 802.3 MAC address, and this is typically seen when you're deploying like a Metro Ethernet switch or an ME3800 down to the customer's box. So like for instance, you instead of deploying a 3925 or an ISR 4400 to the customer's network, you roll out a switch, and that switch has a connection back to, it has a typically an NNI back to the upstream POP, wherever that might be. And then it has a UNI that connects to the customer's network. And then you just simply hand off the connection to the customer, and the customer points the default route to you. And that's typically how you would deal with that. It preserves both the minimum and maximum fragment size of the current .3 standard. It supports a bit error rate better than or equal to 10 to the 12th at the Mac PLS service interface. This has to do with the way that the forwarding infrastructure or forwarding technologies, of the the network adapter. I got internet on the brain. Sorry, the network adapter. How the framing works, and this allows you to be able to scale up with the gigabit Ethernet. Supports provides appropriate support for optical transmission networks, and that's where the high-speed fiber would come into play. Supports a MAC data rate of 40 and 100 gigabits per second, and provides physical layer specifications that support 40 and 100 gigabit operations over various pluggable modules, so SFPs. Transformation to IP. In the traditional architecture, there are numerous parallel services. There is a simple, stable SDH core, and each service is independent. that can be difficult to maintain. I personally would not want to support 100 individual services. That becomes very cumbersome. Think of this like static routing. Why would you want to roll out a bunch of static routes everywhere in your network? Well, you wouldn't, because even with an elaborate static routing infrastructure, there's still issues that could pop up. I personally would move to an IP architecture where everything runs on top of IP. You pull out ATM and SDH or SONET, and you replace that with Ethernet, and then you run IP and MPLS in the core. And that's what we're going to be taking a look at as we move forward. You also have traditional IP routing. Routing protocols are used to distribute layer 3 routing information, which most of you should be already pretty good at that. A forwarding decision is made based on the packet header and the local routing table. So let me ask you a question. Which packet header? And you guys should all be raising your hands and going, ooh, I know the answer to this. Because a packet falls at what layer of the OSI model? Let's think about this for a second. Visualize the 7-layer OSI model and look at the very bottom where layer 1 would be. What is layer 1? That's bits, right? What is layer 2? That's frames, right? That's the data link layer where the MAC address sits. What about layer 3? Which one is that? That is the packet, right? Anything layer 3, you're going to look at the destination IP header, and that is going to tell you where you're trying to go. The destination IP header and the layer 3 header is looked at. If there is anything inside of their local routing table that matches that particular destination, then you can forward it. If there is not, you will pretty much drop it like it's hot. You don't know what to do with it. Think of it like a dead-end road. You've reached the end of your destination. Even though you may be, in a physical sense, you may be driving down a dead-end road. Here in the U.S., there are dead-end roads. I'm not sure about other parts of the world. There are dead-end roads. They're typically marked with a sign called no outlet, which means you can't, once you're on that road, the only way out is the way you came in. Even though there might be some grass and you might see some trees, and then you might see another road, farther away, there's no paved path between the end of that road, and the next road that you may be able to see. A router can't forward data if there's no predetermined path for it. So you'd have to get back in your car, turn around, go back out the way you came in, and then navigate to that road you want to get to. So think of it just like that. Once you hit if there's no route in the routing table, think of that as the grassy end of a road that hasn't been finished yet. Routing lookups are independently performed at every hop. Absolutely. Need to be done, because every router has a different viewpoint of the network. So one router may have a route to something, the next router may not. And you've seen me demonstrate this quite a few times when I've done advertised default routes into things, and I do a trace route to a address that doesn't actually exist in our infrastructure. And I do a trace route to, say, 1.2.3.4. And I get to whoever advertised the default route, because once that router receives that packet, he's going to look at the destination layer 3 header, look in his routing table, and go, sorry, man, I don't have an exit point for you. I don't know what to do with it. So he pretty much just throws it away. And then you get the dot, or the star, from your ping and trace outputs, and that leads you to where you need to go. So if you get that, typically there's a routing problem somewhere. And that pretty much wraps our setup here for the basics of why you would want to move to an MPLS environment.